Hey, what's up, guys? In this video this class lecture is to talk about the Clifford group. So this is somehow like the extra, but it's another extra, right? But I think it's interesting, and this will be the Clifford group. This terminology and knowledge is like really important if you want to do the quantum information research, especially so-called error correction. And error correction is the topic that I will try to cover after a month. But since we already talked about a universal quantum computation, so we need to uh, this is related. Okay, so the main message for this topic is to ask. Right, remember that we say Hadma and the C naught and the T, which is pi over 8 gate. These are approximate universal. So that means that any unitary can be reproduced arbitrarily close to be the product by the product of these three elements. So T is 100 exponential I pi over 4. Okay, so one can define a so-called S gate as a T squared, which is 100 I. And then this is called phase gate because you will just for one cat one, you will just apply additional I. Okay, so one question I asked last time is that whether one can further reduce this into maybe two of them, right? And you need to must have this C naught because it's two qubit, these are two like one qubit state. Okay, so the question what we are going to ask is the following. So we can consider the following gates. What about the Hadamard and the C naught and also S, which is T squared? Is this is this gates like computational universal or this forms a universal gate? So this is a question that I want to ask. If you replace this to be S, which is T squared, are you still is it you still get the computational universal quantum computation? So this is the question that I will answer in this video. Okay. Uh, okay, but in order to do this, we need to further give some math, right? So we define a interesting object called Pauli group. So Pauli group on n qubits is basically tensor product of all Paulis that with plus or minus I phase before the Pauli. And each Pauli is either Pauli X or Pauli X, Pauli by Pauli Z, or identity. Okay, so maybe it's a little bit abstract. For example, for P1, we just have identity X, Y, and Z, or plus or minus I, identity X, Y, and Z, also minus I, minus X, minus Y, minus Z. So there you get four of them. Sorry, total has 16, right? And this is a group. This is a group. Okay. The idea is that you can see that the Pauli is close. The Pauli are close on once you include in this phase, because I know that for example y is IXZ, right? So if I use x times y, then I get IX squared Z, then I get IZ. So if I multiply x and y, then I get IZ, and so I will get IX, Y, and Z. And the Pauli square is identity or minus identity. So that means that this is forms a group, right? You can check by yourself. Okay. So their size is 4 to n times 4, which is 4 to n plus 1, okay, including the phase. And all the elements are either unitary or Hermitian except the phase, right? If you don't care about phase, that's fine. Okay. And this is basic for error correction and stabilized codes that I will not explain here, but we will see in the future videos, in the future lectures. So I will skip here. Okay. So now if we have this Pauli string, this Pauli, then one can define a group called Clifford group, which is denoted as Cn, which is all the unitary such that UPU dagger belongs to Pn for all P in Pn. So this is Pauli group. So in the mathematics, which is all the unitary group which stabilize the Pauli group. So that means that you will map Pauli to Pauli. So U is basically UP, you still become a Pauli, still a Pauli group. Okay, so this is non-trivial. So we will see some example. Okay, so it maps Pauli to Pauli and normalize, basically called normalizer of the Pauli group, which is finite group. This is non-trivial, highly non-trivial. Okay, so why are talking about this? For example, this Clifford group has some interesting elements. For example, all the Paulis belongs to PCN. Right? This is trivial because I know that PN already is a group. So Pauli group stabilize itself by the group close property. So that means that all the identity X, Y, and Z are in the Pauli group. More interestingly is Hadamard, right? So remember that Hadamard will just map X to Z and map Z to X and map Y to negative Y. So Hadamard indeed is stabilized Pauli, right? Because it mapped Pauli to Pauli, right? Hadamard map X to Z, Z to X, and Y to negative Y. So Hadamard stable map Pauli to Pauli. And also phase gate S indeed also map Pauli to Pauli. So you can see this is just so you can see the phase gate is just rotation along the axis. So definitely you will fix Z. And this is the property that one can verify. So I can verify for you. So this is S 0, 1, 1, 0. This is X. It's 1, 0, I. Right. So I can compute this. Okay, so I get it here. So the negative I because this is S dagger. This is S dagger. So it's here. Now I get 0 minus I 0, which is Y. So X dagger is Y. Okay, once you have this, then you can times S squared and you can prove SY S dagger is minus X. So phase case is a interesting guy, right? He maps is exchange X and Y. So this is exchange X and Y. And Hadamard you can view as exchange X and Z. Okay, so for two QB gates, there's a C naught, right? There's a C naught. So indeed, C naught maps Pauli string to Pauli strings. C naught maps X tensor identity to X tensor X. Okay, so how do you understand this equation? So remember that C naught, the property of C naught is that if the first bit flip, if the first bit is 1, the second bit will flip. So simply speaking, if there's an X comes in the first bit, the second bit will flip, right? So if X in the first qubit, the second bit will flip. So mathematically, you should basically say that the X, if there's a first bit flip in X, the second bit should flip. So which maps to X tensor X. You can prove by yourself. You can just mathematically expand it, but this is just intuition. Simply speak, and also if the second bit flip, second bit is a target target qubit, right? So if the target qubit flip, the result is still the same, just target qubit flip, because the first qubit does not flip. Okay, more non-trivial is these two. If you apply Z and apply C naught, you get the same thing at the first. But if you flip the second bit and you apply C naught, you get Z tensor Z. Okay. So I suggest that you can check by yourself. Check. Okay, so this tell you that this C naught preserve the Pauli structures. Okay, and okay, I will not explain why what this means in I will explain in the future lecture, but this already tell you something non-trivial because you can easily check that when you use T gates, this will not belong to Pauli. But if you use a Hadamard and S and also C naught, these three of them they are special, right? They are belongs to the group called Clifford group. So they are not arbitrary unitary. They are unitary with a spatial construction which can stabilize Pauli. Okay. So the indeed is that so indeed what we will show that if you only have Clifford group and some classical control, then there exists the efficient classical simulation. So simply speaking, Hadamard, CNOT, and S-gate does not form the universal gate, does not form quantum universal. And this is famous Gaussian-Cornell theorem, or Cornell-Gaussian theorem. Okay, so quantum advantage requires some non-Clifford gate, like pyrite. Okay, so Clifford group is a normalization of Pauli group, and it's generated by Hadamard S and C9 Paulis. This is non-trivial to prove. And basically, it's not universal. You need a non-Clifford gate for quantum advantage. Okay. Okay. So I'm not provide a rigorous proof. I'm not going to provide a rigorous proof of Cornell-Gaussian, right? Because it's out of the scope of this course. But I will give you a feeling. And but in order to prove, in order to like give you a feeling, we need to like investigate more about this Clifford group. Okay, so the first fact is that I will first give you some elementary property of the Clifford group. So first is a group, because the identity belongs to Cn. If you take two of them, and the multiplication still belongs to this is close, right? And it's very simple. You just take UVP and UV dagger, and you get UVPV dagger, U dagger. Now this guy is still Pauli, belongs to Pauli, right? Some Pauli group. Now, so you get U, P, and U daggers belong to some Pauli group. So finally, still belongs to Pauli. And if you take a Pauli group and take an inverse, sorry, you take a Clifford element and take an inverse, you get U, P, U dagger. Let's say it's Q. And obviously, P is a U dagger Q U, which is U inverse Q U inverse dagger. So map Pauli to Pauli, just exchange. So conclusion is that Clifford is a group under matrix multiplication. Okay, so let's U to be the element in the Clifford group. One can define a homomorphism H from Pauli group to Pauli group. You can map Pauli to Pauli by HP, acting on P is UPU dagger. Right? So basically, it's conjugate map. And identity to identity minus identity to minus identity. And you can see that with HP times HQ is UPU dagger, UQU dagger, right? So these two will cancel. Okay, UPQ, right? UPQ, which is HPQ. So this is why H is a homomorphism. Right, homomorphism, because it map PQ to HP times HQ. If you don't know about homomorphism, you don't need to worry about detail. The map is called homomorphism from two groups. If you have group G and H, there's a map. If there is a map between them, and such that FGH is the same as FG F times FH, this is called homomorphism. Notice that original GH has a group operation here, and so this GH is a group operation inside G, and this one the group operation is inside H. Okay, so this is whole homomorphism. So this is the proof. And notice that all the Pauli, right, either commutes or anti-commutes. So PQ is either plus or minus QP, and the definite HPQ equals plus or minus 1 HQ HP using this property. Okay, so this given Clifford elements, you can create homomorphism. So H is a group homomorphism preserving multiplication and commutation. Okay. So the main theorem, which is non-trivial to prove, is that okay? I will try to prove this in the quantum error correction literature, but in our course. But I will just mention the idea. So the main theorem is that this representation is unique up to a phase. So mathematically, what I'm saying is that if I give you a homomorphism from Pauli to Pauli, let's say I give you a homomorphism from Pauli to Pauli, right? It must exist a unitary such that HP is a forms of UPU dagger, and U is uniquely up to global phase. So this is the non-trivial proof. Okay, so let me see how should I to prove this require like maybe like 2 or 3 pages proof. But I can give you a sketch.